Hello everyone, welcome to this NPTEL course on simulation of modern power systems. I am Abhijit Mahapatra, professor in the Department of Electrical Engineering at IIT Kanpur. This is the first lecture of this course in which we will start with basic introduction to power systems and we'll talk about the recent issues and challenges that exist in a brief fashion. The course would have several modules starting with a well-known steady-state analysis tool called as power flow analysis, in which the aim or objective would be to find the network states having known certain inputs and network topology for a given three-phase power network under steady-state conditions, which will be followed by a well-known, most commonly used tool in industry, power industry, known as contingency analysis, also called as security analysis, which aids in letting the operator know that in case of a contingency, wherein we define those contingencies as set of events that can happen in time during the course of operation and may be detrimental to the overall operation, security, stability of the power network. So what would be those impacts because of those contingencies? To be precise, the line outages, generator outages, those impacts would be seen as part of the the contingency analysis module. The steady-state analysis discussion will be followed by topics on rotor angle stability analysis, both in transient as well as the small signal domain. We will talk about in details why these two terms have their own interpretation and why the same is true from the perspective of rotor angle. Then it will be followed by, so the third and fourth modules would be part of our transient analysis. The fifth main module would be, as the term says, would be part of ultra-fast transient analysis, which majority of power engineers are not very well aware of, but it serves as a very strong backbone for designing of our system to protect it against lightning events. And followed by another voltage stability analysis tool which would form part of the transient study. And lastly, it would end with subtransient study, which is known as the fault analysis. To be precise, AC fault analysis, because portions of DC fault analysis would be covered as part of the ultra-fast transient analysis. So, given that we are going to discuss topics which are relevant to the operation of power systems, to be precise, modern power systems, and each of these topics involves dedicated simulation-based platforms, and that's where the course name comes in, Simulation of Modern Power Systems. As part of this course, we won't be delving deep into details of how the simulation precisely is done for the given power network under these different time domains, steady state, transient, subtransient, and ultra-fast transient. But definitely the understanding of these different topics and modules will create the premise of how actually the simulation platforms like Simulink, PSCAD, Dixilent, RTDS, how these EMTP models, steady-state models, how do they function? The corresponding mathematics, the theoretical understanding of it would come from this particular topics that we will discuss. So to begin with, we all know the evolution of power systems. The need for power systems was generation and load, the electrical load, they need not be placed at the same geographical location, and hence we need a power network which would transmit the power from generating stations to the load ends. Conventionally, the first ever recorded well-known power network was a DC power network established in the lower Manhattan area of New York, thanks to Thomas Alva Edison, which was primarily meant for lighting purpose. 11,000 bulbs were being electrified for 500 customers. The voltage level of this DC system was initially 110 volt, which was later upgraded to 220 volt. The reason for this upgradation was at lower voltages, the corresponding copper losses, the copper conductors which were used to lay out the corresponding power lines, in those copper losses, in those copper underground cables, the losses were significantly higher, and hence Edison thought maybe by upgrading the voltage level, these losses would go down and more power becomes usable to these lightning load, the bulbs. However, because I square R loss even at low voltages was substantial, and hence there was a failure, and eventually the Pearl Street station, which was a primary substation for the distribution of the DC power to the lower Manhattan area, it got burnt, and eventually in 1895 the entire system got decommissioned. Parallelly, the AC system devices like transformers and induction motors, their concepts and designing and theory were also coming up, and eventually people realized that it's time to move to AC system, wherein the loss component, the voltage drop component can be minimized thanks to the use of the transformers, and the DC motors being replaced by high performance induction motors, where the electrical loads, the industrial loads also felt they could make more profits, have more savings if these were to be replaced by the DC motors were to be replaced by the induction motors. So the first ever AC power network, which was recorded or which was known, was established in Oregon City in 1889. Two 300 horsepower hydro generators were used to generate the power, and the loads were mostly in the Portland area, where the power was transmitted through a 21-kilometer transmission line operating at 4 kilovolt. The operating, and then the first three-phase network came up in Germany with a line of 179 kilometer at 12 kV voltage level. And while all this development was going on, there was no standardization of the operating frequency. The AC network will have a frequency. So there was no standardized frequency. Frequency varied from 25 hertz to all the way till 130, 133 hertz. And across the globe, there were different AC power networks. Forget about their interconnection. There were different AC power networks across the globe operating at different frequency. Over the time of operation, what the consumers realized that at low frequencies or low frequency of operation of AC power network, the electric incandescent bulbs or lamps, in them, since the frequency is low, the corresponding flicker which was observed, that was very visible or pertinent to the human eye. Corresponding 25 hertz refers to a time period of 40 milliseconds, and as the frequency further goes down, this time period goes up, and hence at lower frequency of operation, almost there was, so basically one full cycle in AC would refer to a 40 millisecond time operation. The delay was very perceivable to the human eye, and eventually it was a discomfort, and consumers often complained about this flicker or visible variation in the light luminosity which is being observed. And hence engineers thought that, okay, let's increase the power frequency, and that would help in reducing this discomfort of flicker. And then if frequency has to be increased, to what extent can it be increased? Another important part with system frequency is, as frequency goes up, the corresponding device sizes like transformers, induction motors, their cores, stator core, rotor cores, the transformer cores, their size could go down, but corresponding loss component in the eddy core loss and other losses, they also tend to likely go up. So as engineers, one has to have a trade-off between the visible flicker and the corresponding designing component, the cost involved, the capital investment in designing those setups and commissioning those networks. There had to be a trade-off, and eventually it was realized that the sweet point of frequency at which this flicker would be very negligible and the system design would be very efficient, that frequency was observed to be 60 hertz, which is well-known standardized frequency in US and Canada. And for the rest of the world, India and other nations, we settled at 50 hertz because for us 50 hertz was a good enough point. The electrical trade-off analysis details would be available. Therein people thought that 50 hertz is fine for us, and hence we will settle at 50 hertz. Interesting question that comes is, why is there a difference in the 60 Hz or 50 Hz? Technically, there is no precise answer for that, but different references, different literatures do point out to different reasons, and one tends to settle down at the reason which one is comfortable enough or reasonable enough. So as a result of these different operating frequencies, definitely interconnection and parallel operation was not possible, and hence standardization was necessary, which is where we settled at 50 Hz and US and Canada at 60 Hz. Coming to the evolution or history behind Indian power system, to some extent thanks to the Britishers for their visit to India and having helped us set up this idea of electrification. Details of this history could be very well found in this resource paper, which is IEEE conference paper. 1879 in Kolkata, the first DC power network was set up. And then the first hydro power installation was done in Darjeeling of rating of 130 kilowatt. The first thermal power plant came in Imambagh, Kolkata, of rating of 1 megawatt. And eventually post-independence, so till independence, all this was being done in an ad hoc fashion, but post-independence, we the Indians, we realized that we need to have standardization, and hence 1948 Electricity Supply Act came in, which the motive behind that was to modernize the electric network that we have had and bring in uniformity. As a result of which, different states that came up as part of the Constitution of India had different electricity boards where they were given the responsibility to regulate their own power generation, transmission and distribution. And at the national level, we had Central Electricity Authority to sort of oversee the planning and operation of the entire Indian power network, which was still disintegrated. Interconnection was still not possible. And over time, the Electricity Act has been amended. 1975, the amendment led to the foundation of National Thermal Power Corporation, Hydropower Corporation, and Nuclear Power Corporation of India Limited. All these were generating companies. Their primary focus was to see the overvision of generation, local generation, and the eventual transmission. But as the electricity demand increased in 1989, Electricity Act was again modified or sort of changed, which led to segregation of NTPC into usual NTPC, which is where they were responsible only for generation aspect, and there was this dedicated third-party unbiased fair entity which was called as Power Grid Corporation of India Limited, which was supposed to oversee the planning, operation and maintenance of the Indian network grid that we have had between these different states. Again, in 2003, the Electricity Act was sort of changed, amended, and it superseded all the previous acts and amendments, wherein CERC came into existence, another body parallel to CEA, which would be a regulator for the operation of Indian power network. CEA is the planner, CERC is a regulator. And if we had planners, regulators, we need to have our own operators, which is where POSOCO came into existence in early 2000. And then eventually POSOCO has also been transformed. So PGCIL got broken up into PGCIL for maintenance and planning, whereas POSOCO, Power System Operation of Corporation of India Limited, was responsible only for the operation part as devised and dictated by the regulators. Indian power network, it's a very interesting country. We live in a diverse nation, and hence our nation so far as post-independence, I would say, has evolved into 5 regional grids. This diagram here shows those different colored grids, as you can see from this reference also. Since these grids were all disconnected initially, the first interconnection which happened, these 5 regional grids, they were not interacting among each other. Each grid before 1991 was responsible for its own generation, for its own transmission, and for its own consumption. There was no cross interaction of power or energy between these grids. 1991, the northeastern grid and the eastern grid got interconnected, in which then in 2003, the western grid also got connected, and in 2006, the northern grid also got connected. Till this point in 2006, interconnections were feasible, and the entire Indian power network was operating in synchrony, except the southern grid, which after a lot of efforts, planning, operation, lot of brainstorming in 2013, finally our country became one single national grid, wherein we had one single national frequency. And since the frequency is same, we call that grid to be a synchronous grid or one nation grid. Typical voltage levels in India vary from few tens of volts to few hundreds of kilovolts. So our generation typically happens at few tens or twenties of kVs. Transmission of power at such low voltages would not first transmit to large lengths, and eventually if it is to be transmitted, the corresponding losses are to be very high, and that's where we have the transmission system where the same power, if it is transmitted at a higher voltage level, transfers to a larger length with lower losses. And then eventually at the load end, we do not have appliances, or it's not safe to have appliances which would consume power at such hundreds of kilovolts, and hence we have the distribution network where the voltage gets amped down, and eventually the consumption through this distribution sub-transmission network happens at 415 volt three phase or 230 volt single phase. We have a very ambitious target of reaching 500 gigawatt of renewable energy generation by 2030. We are making, the country in itself is making good progress, and there are good plans that we will be able to reach close enough to this number. Having set this target, it's interesting to also see what's the installed generation capacity in India has been across the years. So over time, if I make a reference to the data which is available or maintained by CEA on its website, the link is given here, compared with the data that was present on January 31st, 2025. By the way, every month CEA updates its report on installed generation capacity. It's a very interesting exercise to see how the numbers change. So with reference to January 31st, 2025, if we talk about the situation which was there a few weeks ago, May 31st, 2026, the table here shows those distinct numbers. January 31st, 2025, we had an installed capacity of around 466 gigawatts, whereas over a year and 4 months, that same 466 gigawatt has increased to 542 gigawatt, with renewable share, overall renewable energy share, going up from 35.4% in January 2025 to 42.55% as of on May 31st, 2026. The current number that we have for renewable energy generation is 230, or I would say 231 gigawatt. We have already crossed half the limit of 500 gigawatt, which we aim to achieve by 2030. And hence, since we have crossed that number, it is hopeful that we will be overseeing or checking this to be close to 5 lakhs megawatt by 2029, 2030. And interestingly, another number which you would see is we do have thermal generation, which in January 2025 resulted in 52.7% of share in installed generation capacity. The numbers here, if we see compared to January 2025, these numbers haven't changed much. They are more or less the same as it was there on this date compared to the present scenario. But since the renewable percentage has, or the renewable share has gone up, that's where we see a decrement from 52.7% to 46.25%. The other numbers in terms of hydro generation and nuclear generation, they are pretty much the same, and that's how the trend has been. So out of 442 gigawatt of installed generation capacity, this 542 gigawatt in no way refers to the peak demand that we see in India on a national grid. It only pertains to the overall installed capacity that is present as of now in India, 542 gigawatt. And this amount of power is very sufficient enough for the current load that we see on an average daily basis. Of this number, the corresponding share, which is sort of the plants, the generating plants, almost 24% of those plants are owned by the state governments, the state utilities. Close to 53% is owned and operated by private entities, and remaining 23% is coming under the domain of the Government of India, the central government, the central sector. And of all these numbers that we see, if we have to sort of figure out the overall performance, the overall utilization of this 542 gigawatt, our thermal load plant factor has been close to 65%. Ideally, if it is close to 100%, it would indicate that whatever power is being generated, the same power is being utilized over a year, over a week. Generally, the thermal load plant factor is calculated over a year. So the numbers are still low, reason being the renewable generation has come up and this number is only for the thermal plant. But overall, at the outset, we as electrical engineers should aim or have designs or proper system operation and utilization so that this number tends to reach 1 or 100%. Coming to the notion of smart grid, the diagram that we see here, the corresponding light colored blue lines, they pertain to the flow of power in a conventional power network where the power flow was all from one end to the other end, from generation to the residential, commercial and industrial loads. With evolution of smart grids, which talks both about the electrical power network as well as the communication infrastructure, controllability came in, and with the development of renewable energy resources, the flow of power was no more unidirectional. In fact, distribution networks, thanks to electric vehicles, storage devices, microgrids, wind farms, solar rooftops, all this can result in excess of energy at the distribution end, which can backflow from the distribution network through transmission network to another parallel distribution network, and hence energy exchange can happen efficiently. That's what is meant by the bidirectional power flow. And the devices, thanks to intelligent ICT network, internet and communication network, these devices also interact or send signals among each other in terms of energy, voltage, current, and the corresponding control action can also come in, which is what is making this network smart, in the sense it is able to perceive changes, it is able to have interaction and brings in transparency in terms of overall system operation. Some of the trending concerns that do come in because of the discussion on smart grid is renewable energy integration. Renewable energy integration, be it solar, wind, storage, these generations are dependent on weather, and hence their generation or injection is uncertain and variable. So the difficult question that comes is how do we handle or operate the system under these uncertainties? The system cannot wait for the uncertain event to unfold and then some corrective action happens. As operator, one has to also look at the overall security and economy given these uncertain variations. Because of renewable energy integration, the overall grid stability has also been affected. We will talk about it in detail when we talk about the rotor angle stability analysis when we define the grid inertia. Grid inertia is essentially a measure of the stored kinetic energy in the system divided by the overall generation capacity. So with integration of more renewable energy resources, the grid capacity has gone up, but majority of renewable resources such as solar power or battery storage, these devices do not have any rotating part among themselves, and hence the corresponding kinetic energy ratio has gone down, which in a way tends to bring down the grid inertia, and during disturbances this inertia plays a very important role. Basically, it gives a measure of how resilient is the system in case of disturbances. Because of these renewable energy integration, there are requirements in terms of infrastructure for upgradation of operation, protection and control. We don't have yet standard operating procedures of how to understand and analyze whether our power network is ready for EV technology. Distribution networks, as I mentioned, have become bidirectional with bidirectional flow. So network design conventionally has been that transformer would only transfer power from high voltage to low voltage. But with more renewable being integrated into the distribution network, there is possibility of flow of power from low voltage to high voltage. So how is that transformer designed? How the transformer life gets dependent? It also all depends on this. Having different bidirectional flows, distribution networks also need to have their own operators, and like POSOCO or Grid Controller of India Limited is the default transmission system operator in India. There is still no standard operating procedure for distribution system operators, where under a given operator there will be different distribution networks who would generate power among themselves and exchange them. And then eventually the TS would also have to interact or communicate among each other in terms of this power exchange. Our demand has not been that flexible as it was expected to be, thanks to, or sort of the idea behind demand response is good, but the implementation is still far from realization. We still don't have sufficient measures for ancillary supports from renewable energy resources. Ancillary support refers to the capability of a renewable energy generation being able to provide voltage support, frequency support, endure a disturbance, reduce congestion. All those capabilities, aspects, they are still not up to their mark from the renewable energy integration perspective. So in terms of overall system operation, our power network is one of the most complex man-made network with several interconnections, with several elements, generation, transmission, distribution, and loads. There are several utilities which are present, dedicatedly present for monitoring, operation, and regulation of these different generation, transmission, and distribution. Except for the transmission system, which is coming under the domain of Grid Controller of India Limited. All other entities have got their individual private players. In India, transmission system still comes under the central utility or central government. We have 5 regional load dispatch centers because of the 5 regional grids, and on top of these regional load dispatch centers, RLDCs, we have 1 national load dispatch center present in Kathuria Sarai, New Delhi. We also have 2 power exchanges which aid in exchange of energy and power between different generators, private players, utilities, and loads. These all came up in 2008, and these are basically PIXIL and IEX. In terms of attributes of a good power system, given that the network is a man-made network, so we human beings, we all tend to achieve perfection. And in order to have perfection in a power network, so what all attributes that we should look into, the same has been explained here. The first important part is economics, whereas wherever designing of a system is involved, money will be invested. And hence, economics has to be good so that the money is recovered, the overall system operation is at its lower minimum possible. Stability is an important concern, wherein during disturbances, deviations, contingencies, system voltage and frequency should not change, even for varying load conditions. During uninterrupted or unexpected situations like outages, system still should run in a secured fashion, in the sense system operation, the voltage level, frequency level should not deviate or go beyond desired values, at which case the relays start operating and then the system security is at stake. The loads get interrupted. In terms of downtimes, a system is called to be reliable if its interruptions as low as possible, maintenance time is as low as possible. During events such as natural disasters, whether the network is capable enough of recovering from faults or disturbances due to natural events or natural hazards, and still be able to recover or come back to its normalcy state, that attribute is called as resiliency. And lastly, we have quality, wherein we tend to talk about minimization of harmonics because of the renewable energy integrations. All these different attributes that I have briefly talked about, there are dedicated tools available or exercises which are done as from the operation perspective, and all this is done through a platform known as energy management system. The EMS can have different terminologies. In distribution systems, we call it that DMS, TMS, and so on. But overall, the concept is that it is in these EMS systems present at control centers in which the dedicated tools are done or analyzed or exercised while trying to maintain these attributes. In terms of protection, it is essential for the network to prevent the system or protect the system from detrimental events such as faults. Every electrical fault has unique characteristics. The 2 characteristics are, during a fault, the current will tend to go up, whereas the voltage will tend to go down. As electrical engineers, we should also think that, okay, why a fault always has this behavior? Why can't a fault have a behavior like current tends to go down and voltage tends to go up? In that situation, will the fault still be detrimental? please think about it. We'll talk about it in details when we talk up the module on AC fault analysis. Every protection system either has fuses or has certain transformers which sense the electrical voltage and current, and then this information goes to the relay, where the relay processes this information and then issues a corresponding trick signal, which the trip is done through the circuit breaker. From protection perspective, it should be very simple in logic, should be accurate, should be reliable, and clearly or fastly trip up the faults. In context of recent challenges, AC protection and DC protection, these two are different entities. So first of all, why do we need DC protection? Over time, DC microgrids, DC grids have also come back from their sort of last long retained history of Alva Edison, where AC came up and then DC was forgotten. But over time, DC networks are also becoming popular thanks to their flexibility and flexibility in operation. So compared to faults in DC system versus the faults in AC system, the issue with DC faults or DC protection is that in a DC network, the current rate or rise is exponential, is very, very high, in fact it is linear, and then tends to go up if it is not checked. And it is all because of the inductance present in the DC cable. The other point in DC protection or DC faults is, unlike in AC systems where our signals or voltage and currents are sinusoids and hence they have zero crossings, in DC system there is no zero crossing at all. So in case of clearing of a DC fault, the corresponding breaker which is to be used, it has to open the circuit even at the condition where the current is still not at zero. In AC systems, we look for a soft point time where the current is crossing to zero and then the corresponding breaker opens so that the quenching is as minimum as possible. In DC systems, the corresponding breakers have to be specially designed so that even at non-zero zero current crossing where the current values are very high, quenching is a big concern, and hence corresponding breakers are excessively different and costly compared to the AC protection part. We'll talk about all this in detail as we go deep into ultra-fast and fault analysis. In terms of analysis that we would see, I think I have explained this a bit in the opening discussion. In terms of power network, we all have to sort of focus on the term analysis. So why do we need this analysis as engineers, electrical engineers? What is the importance of this analysis? Why are we trying to learn this topic? The idea is that given a network, if something changes or even if it is not changing, how good our system is, what are the values of voltages, currents, power flow, energy exchange, frequency, how all these values are to be evaluated. The corresponding mathematics behind that results in this analysis of power network. That is the overall aim. Now, as engineers, we should also think, okay, fine, I have a network, I know what I am trying to find at. I'll use the same technique irrespective of the time of operation of the network and try to find the best possible accurate value of that number. Absolutely okay. As engineers, we should always look for accuracy, but then behind accuracy, we also would likely invest a lot of time. So often what happens is the way power network operates, if an event occurs and that impact of the event has already come in and gone by, and our mathematical analysis gives us the solution which results of the same event impact, but after a lot of delay, then there is no need for that mathematical analysis that we have learned that. We also have to look at that our analysis should be simple enough. It should give us a number which gives the same impact analysis as the actual event is unfolding within the limited given period of time. So time plays a very important point, and that's where the different analysis, steady state, other aspects come in. So as the term steady state, it would mean that time is at all not bringing in any variation. Our network equation, they are all algebraic equations, simple equations, and we can use lumped system parameters. We'll talk about lumped versus distributed when the appropriate time or the module comes in. And the idea behind the steady state analysis that nothing is changing with time, so we want to just find the voltages, power values, loads and so on, and which is what is part of the power flow analysis or contingency analysis. In the next time frame is a transient where time varies in order of few seconds to few minutes. We have a significant difference here, and hence our network analysis needs to also cater to this change in network with respect to time, which is where additional differential equations come in. And the applicability of such analysis comes in transient rotor angle stability analysis, followed by the subtransient period where time window further goes down and we have to model our system more precisely, more perfectly, wherein we use linearized system equations because the time is so small that if we try to solve a nonlinear algebraic equation, the time would not be sufficient to give us that same number. So we tend to resolve to linearized system equations while trying to maintain the lumped system representation, and the idea is to find the breaker currents, the ratings for the relays, and application is in the fault perspective. The last part, which is often not very well explained or discussed, is the ultra-fast transient, where the time is furthermore smaller and our analysis has to be so fast, it has to be so quick that we cannot no more use the lumped representation. We have to go to the actual network representation, which is distributed. By distributed, I mean that if I have a conductor, let's say a wire, assuming this pen to be a wire, and if I have to precisely identify that along this wire where is the physical location where the entire network resistance is represented. As engineers, we often represent this wire through a small zigzagged circuit, and we assume that the zigzag portion refers to the entire resistance, whereas the portion beyond that zigzag wire is a perfect conductor. Ideally speaking, if I break this wire into two halves and still measure the resistance, those two wires will still have the equal number. And I try breaking this wire into a minuscule system element, it will still have the same per unit resistance as this entire wire has, which means that every small section of this wire will have a resistance which is distributed, and that's why I call the actual network representation to be a distributed network representation. Ultra-fast transient analysis would involve such analysis, and eventually it helps in insulation testing and protecting the network during lightning and switching events. So in general, our overall power network analysis is all about trade-off between accuracy and the time involved in getting that value. So what we do is we understand what type of analysis we have to use and accordingly model our system components, write the corresponding algebraic, differential or linear coupled differential equations, figure out a solution technique which would solve these differential algebraic linear equations. After the solution has been obtained, analyze the solution and find other variables or values which would help in understanding what the impact has been, how do you plan a system, how do you make the corresponding decision which would protect your or prevent your system. The next lecture will talk a bit about basic circuit analysis, given that we are going into the analysis part. So we will understand a bit about basic circuit analysis, and then we will go deep into the differences between circuit analysis and the first module, which is the power flow analysis. Thank you.